Hello everyone. Well, actually, after a long time, my system to produce nitric acid from air is finished and it's working. It's actually working very well. So before I go into the details, I want to give you some basics of the system. And well, here it is. The first basic is, well, it's working. It's working very well. I was able to sort out all the issues and all the bugs that were in the system. The second point is it has a power consumption of about 5,000 watt when it's running. The third point is that I can produce up to 20 liters at once, meaning that's the 20 liters of low concentration HNO3 that needs to be further concentrated by distillation. And after distillation, it will yield about 2 liters of the azeotropic HNO3 at a production time of about 12 hours. So let's talk about the core components of the system. The first core component of the system you can see here, that's the actual plasma chamber. The second core component is the high voltage system that you can see here. So this is part of the high voltage system, this is part of the high voltage system, this is part of the high voltage system, and even down here, this is part of the high voltage system. The third part is the water cooling. The water cooling consists out of the water pump that you can see here, the air cooler, so the water flows through that cooler and air blows through, so the water gets cooled down. Additionally, the plasma chamber that you see here is water cooled. The IGBT full bridge is water cooled. And yeah, that's it. Another core component is the hot gas cooler, which we see here at the back side. This is the hot gas cooler. I will explain a little bit later, more in detail. And the last core component that you can see here, they are these two gas wash bottles that will hold about 20 liters at once to scrub the NO2 and form HNO3. So now let's go to the first one, back to the plasma chamber. So the basic idea or function of the plasma chamber is to burn a hot arc while blowing air through the chamber. Air consists mainly from nitrogen, so N2, and oxygen, O2, and some other gases. So the arc will tear apart some of the N2 and also some of the O2 of the gas. So in the end, then we have some nascent N and some nascent O atoms flowing around in the chamber, and those atoms will combine subsequently to form NO gas. And the NO will further react to NO2, to nitrogen dioxide. So the NO2, this is the gas that we actually want as it reacts to NO3 with the water. So apparently there is also some little ozone, O3, and some minor quantities of other compounds generated, but they do not need to concern us. The plasma chamber consists out of the following parts. Here, what you can see, this is the outer electrode. This is grounded, so Actually, during operation, we can touch it and nothing will happen to us, or to me actually. Then we have the inner electrode. That's the dangerous one. We see it down here. You know, this is the inner electrode. So it's a dangerous part. If we're going to touch it, then that's it. And then we are having, as another core component of the plasma chamber, we are having the insulator. The insulator consists out of POM plastics, and in the middle there is a borosilicate glass tube. Actually, in the beginning I thought it's just sufficient if I just take POM as insulator, but apparently it was not sufficient, because after some time of operation there was a crawling discharge, and this crawling discharge totally destroyed the POM. So it was necessary to incorporate something better than plastics, and this was just simply borosilicate glass that you see here. So if you look through the screws here, you see a tube. That's basically a borosilicate glass tube that's submerged in between two discs of POM plastics, and the lower one is holding the inner electrode. In order that you can understand it a little bit better, you know, I have here some drawing of the outer electrode and the inner electrode. So basically, you know, this all in here, this is the plasma chamber. And what you see here, this is the inner electrode, and basically here is the outer electrode, the water-cooled electrode. And within the area where we have the water, so at the outer electrode, you know, we have also some magnets inside. The magnets, they're important because they will swirl around the plasma inside the tube. So they increase the area where the plasma is burning, basically. So more oxygen and nitrogen atoms will basically get ripped apart and recombine again due to the magnets. And so as you can see, the outer electrode is water cooled, so we have water flowing here. And the inner electrode is air cooled. So there is a tube, and inside the tube is another tube. So at the outside tube, we have air flowing up, and then the hot air goes back down the inner tube. Additionally, one part of the inner electrode is this here. You know, it basically makes one spot where the distance is rather small. So here basically the arc is initialized, and because the air is blown in that direction, the arc is also blown up slowly. Yeah, it goes up here, and it will burn at the magnets. Here it will start to swirl around and starting to rip apart the molecules. So what we can see here, down here, that's the air cooling of the inner electrode. So here is the air inlet, and here is the air outlet. And the air that goes in, it has room temperature, so about 20 degrees. And the air that comes out has about 50 to 60 degrees. So it's still suitable to use normal PVC tubing to contain the hot air. And so let's go to the other side. the air actually is sucked in here. So here is a little filter, you know, there's a kind of a filter tube, and the air goes here to the air pump, and then from the air pump the air enters the inner electrode, so the outside of the inner electrode. Then the air goes up, is heated, basically the inner electrode is cooled, and goes down here. Yeah, so here the hot air comes out, and the hot air enters finally the plasma chamber. So here, I hope you can see it. Here is the entrance, the air entrance of the plasma chamber. And at the same time, I show you here, this is the exit of the plasma chamber. Come on. Yeah. And the air that's exiting here is actually already very hot, so it has about 300 degrees. You can also see it because it's a copper tube that comes out there, and on the copper tube there has already formed some copper monoxide, which indicates that whatever comes out there is actually pretty hot. And yeah, that's it. So that's the basic explanation of the plasma chamber. So let's continue. Now we're talking about the high voltage system. The high voltage system basically consists out of two high voltage sources. The first high voltage source we can see here. It consists out of a 4-piece mod stack. And this high voltage supply, or this high voltage system, is basically delivering a low frequency, high current, high voltage. If you stay at this system, you know, the problem with microwave oven transformers is that they overheat pretty fast. So I had to do a lot of things to kind of make them suitable for long time operations, like for example adding some air cooling to it and stepping down the operation voltage with a variac. So down here you see a variac, and this variac is basically doing nothing else as to limit the voltage or step down the voltage to prevent the microwave oven transformers from overheating. The second high voltage, high frequency power supply, you can see here. Actually, the transformer you can see because it's immersed in oil, but it's basically a rather large ferrite core transformer that is driven by a full bridge. So this part here that you can see is an IGBT full bridge. There you see the IGBT blocks, and yeah, so it's basically the driver for the ferrite core transformer. And down here you see the power supply of the full bridge. It's two server power supplies combined. Each one of them has 3000 watt and 48 volt. So in total I have 96 volt to run the full bridge that you can see here, and the full bridge is driving the ferrite core transformer. So that means now we are having a 50 Hertz source of high voltage and about 30 to 50 kilohertz source of high voltage. And how to combine those two high voltage sources? I simply made a way to switch them in serial and to simply bypass the microwave oven transformers with a capacitor, and that was working surprisingly good. So this is it's a capacitor that is used to simply bypass the microwave oven transformers with the high frequency, high voltage from this transformer, and that seemingly works pretty fine. Okay, so we are going to the next system. Just a second. This system. Okay, now we are talking about the water cooling. Again, here is the water pump, and you know the water pump, because there is quite a long tubing, the water pump needs to be dimensioned accordingly, meaning don't use a 40-watt water pump. This is a 180-watt water pump, and it's good to the power is sufficient for the long tubing. I wouldn't recommend to choose anything lower than 180 or 150 watt for projects with long tubing. Yeah, and I told already that the parts of the full bridge, like for example these IGBT devices, they're water cooled, and of course the plasma chamber is also water cooled. And here at the back side we see also a part of the water cooling system. It's this tube here, and I call it the equalizing tube, because this kind of thing is necessary in water cooling systems, because when the water changes the temperature, it will change the density, and the water level will rise up or go down when it's cooling. Another essential part of the system is the gas cooling tube that we see here, because the gas that comes out of the chamber, you know, it comes out here and goes here. It's rather hot, you know, it has about 300 degrees, and that is why gas cooling is necessary. Otherwise, you know, if we would take the hot gas and directly bubble it through the water, we would have a crazy rate of evaporation. So for this, in this sense, it's necessary to cool it down. And I had actually a good idea, and it works really well, how to cool the gas down sufficiently. I just took a tube, stainless steel tube. It's about 1 meter, and I have simply filled the tube with this stainless steel sponges. And the cool thing about it is that they have a big surface area, and it is very likely that the gas molecules that are hot collide with the stainless steel sponge, and they will give its thermal energy to the stainless steel sponge, and the sponge will simply radiate the energy out to the walls of the tube, and the walls of the tube will simply radiate the energy then to the air. So when I run the system, you know, the top part is, you will burn your fingers when you touch it. The bottom part, the gas is already that cold that you can touch the tube. And basically from here, because there is still some residual temperature, I used to take a Teflon tube, even though it wouldn't be necessary. I could have used a normal tube. And the next thing that you see here, it's simply a water trap. So when for when for some reason, when there is a negative pressure on this side, could happen to I don't know what, the air, not the air, the water will not be sucked back into the system, you know. So this is an additional protection mechanism to prevent water being sucked back. And you know, the last component of the system, they are these two gas wash bottles. Each gas wash bottle, or each gas wash tube, can hold about 10 liters of water. So basically the gas is immersed here. Within the tube there is a long short tube that goes right to the bottom, and the gas is pushed under a stainless steel sieve, and the gas will then go through the stainless steel sieve and bubble up through all the water, you know. And in that kind of way the nitrogen dioxide will react with the water and form nitric acid. And yeah, so I found out that about 12 hours is an ideal time to run the system and simply to perform the distillation after 12 hours, and that will yield to about 2 liters of the azeotropic 68% nitric acid. And this here that you see here, it's the exhaust tube, because there are still some nasty gases inside, like ozone and some not reacted nitrogen dioxide or whatever kind of other gases. And they are simply pushed outside of my workshop. And yeah, that's it. So now we're going to run it. I have to plug it in. You hear already that the arc is burning, fans are on. Here I can see the frequency that the full bridge is operating, so about 40 kilohertz. And the loud noise that you can hear is the air pump. And this is already getting hot. So I want to demonstrate to you the evolution of or the production of NO2 gas. For this reason I just direct the NO2 gas in a barrel, and we're going to check this out now. So this is the inlet tube here, and there we go. That's 5 minutes. I have to hold my breath. NO2 gas is actually pretty toxic, so I shouldn't do that without a respirator, but I will simply hold my breath. Come on. I want to go a little bit more in detail how things work to try to make things clearer. And yeah, let's start with the plasma chamber. So here I have drawn a schematic of the plasma chamber, and let's begin, or let's have a look at the outer electrode. So the outer electrode is basically this here. It's water cooled, so it has a water inlet and a water outlet. And actually, in the area, yeah, where the water is flowing, there are the magnets. They are just normal, actually very large sized ring magnets that you can find, for example, in sound systems, in the loudspeakers. I just, I bought the biggest one that I could find. They have a diameter of about 100 millimeters, so 10 centimeters. And the gas outlet, so where the hot gas comes out, is at the top of the chamber, and the gas inlet is somewhere in on the lower side of the chamber. And now let's come to the inner electrode. So the inner electrode consists out of two tubes. The outer tube is at the top, of course, closed, and the inner tube we are having inside. Yeah? And you can imagine that if here in the outer tube the cold air goes in and it goes up, it heats up while it goes up, and then here the hot air comes down again here. So as I already told, the hot air has a temperature of about 60 degrees, 60, 70, whatever, when it comes out here. And of course the outer electrode and the inner electrode, they need to be isolated from each other, and isolation is a big topic. I have told already that at the beginning I just had a plastic plate, a POM plate, to insulate those two electrodes, but it wasn't sufficient because there are some crawling current discharges, and they basically destroyed this plate here. So I have introduced a borosilicate glass tube in this area, and glass is much more suitable to insulate than this sort of plastic. And I forgot to say here, so this stuff that you see here, I've made it out of brass, but you can do it from whatever material you want. Stainless steel would work too. It's there to ignite the arc at a specific defined position, because without that, the arc could just ignite anywhere, if it would ignite at all. And you know, this distance, so the shortest distance should be not more than 5 millimeters to make an easy ignition. And the distance between here and between here um, should be about 3 centimeters. You know, and when the gas flows in here, it will subsequently, once the arc is burning, it will blow the arc further up. The arc will rise up here, and eventually, due to the magnets, the arc will stabilize and just burn in this area. And through the magnets, it's flattened out and rotating very fast, which is good. So I hope that the design of the plasma chamber is clear for now. Yeah, so let's continue, let's go on. Here we are at high voltage supplies. Again, I have told there is this high frequency supply and there is this low frequency supply. And basically, in order for the high frequency supply to don't damage the low frequency supply, there is a bypass capacitor. Actually, you know, when I would redesign the system, then I would simply scrap this part here. You know, the mod stack isn't really necessary. I just left the mod stack because that's how I started with. I thought that's a good idea. In actual fact, the mod stack it's not a good idea because it takes a lot of work to get it working, and you have these thermal problems, and it's really a lot of work. So I would just recommend to, you know, invest the time for making a decently good high frequency, high voltage power supply using large ferrite core transformer in oil with a proper full bridge. Actually, to build the full bridge, it's some sort of a lot of effort. You know, I kind of worked at least 1 month on the full bridge driver, on the GDD driver, and there were lots of lessons learned and errors I've made. So what I would suggest, or if I would do it again, I wouldn't build it myself. I would simply go to AliExpress, type in full bridge SSTC. SSTC stands for solid state Tesla coil, and they have, you know, for decent prices, they have quite a lot of course, low power full bridges here, but I don't know, that looks like 1 kilowatt or 1.5 kilowatt maximum. But they have also some high power devices, for example here for 508 euros. That's basically using the same IGBT blocks that I have used for my full bridge. Having also the GDD there. And yeah, basically I simply would use ready-made solution, and I'm pretty sure it's possible to find something on the market, not to build it myself, because this was a lot of work. Okay, and this side, you know, the outer electrode is grounded, that I've also told already, and the hot end is the inner electrode. Good, and let's go on to the schematic of the airflow. So we started the air in the room. The first step is the dust filter. The second step is, of course, the air pump. The third step is the air cooling of the inner electrode. I've shown this already here. So the cold air is going in here and the hot air is coming out here. Okay, there we are. cooling of the inner electrode. Then there is the plasma chamber, then there is the gas cooler, then there is the water trap, and then there are the gas wash columns, and then there is the exhaust. So pretty straightforward how the air or the gas is moving through the system. And for the last flowchart here we have the water system. So the flow of the water is in this direction. First of all, we have the pump. The pump is pressing the cool water through the plasma chamber, and then through the full bridge, then it goes into the heat exchanger, then into the equalizing tube. Yeah, that's basically it.